Hi everyone, I am Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So, overview of today's presentation, start with introduction of configurations. So, we have common base, common emitter, common collector configurations of the BJT, and particularly we mainly focus on analysis of common emitter configuration, CE configuration, and we will see some transistor parameters or performance parameters of CE configuration, and we will conclude with summary. So, let us start. What is transistor? We know transistor means transfer resistance, as the signals are transferred from low resistance region to high resistance region. And transistor BJT is a 3-terminal 2-junction device. The 3 terminals are emitter, base, collector. So, here emitter is heavily doped and base is lightly doped, collector is moderately doped, and physical size of collector region is more because it has to dissipate more power compared to other terminals. And here the BJT has 2 different types of transistors have. Operation depends on both majority and minority charge carriers. Hence, it is called bipolar, and the 2 transistors are NPN and PNP transistor. So, here you can observe the block diagram. So, this is NPN transistor and this is PNP transistor, and here you can observe this is NPN transistor because emitter current is flowing out of the transistor, IE. So, this arrow indicates NPN transistor. If the arrow is into the transistor, that is emitter current is flowing into the transistor, then we can say it is a PNP transistor. So, today we are going to discuss about different configurations. We have common base configuration and common emitter configuration and common collector configuration. So, these are the setup for the different configurations of the BJT. So, this is common emitter configuration because emitter terminal is grounded here, or in other words we can say emitter terminal is common to both input port and output port. Here this is common base configuration because base terminal is grounded. In other words we can say base terminal is common to input port and output port, and this is your common collector because collector terminal is grounded, or we can say collector terminal is common to input port and output port. In other words, we can say common emitter can also be termed as emitter grounded configuration, and this is base grounded configuration, and this is collector grounded configuration. So, these are the 3 different configurations. Now, today we are going to focus on common emitter configuration. So, common emitter configuration. So, let us see the description of this. The emitter terminal is connected to the ground and the input is applied between base and emitter junction, and the output is taken between the collector and emitter junction. That means, so we have, this is your transistor. So, let us say NPN transistor. This is base, collector, emitter. So, common emitter means emitter terminal is grounded. So, that means emitter terminal, this is input side. So, the input is applied between the base, this is base and emitter. So, across this you apply some input voltage, right? Then, what is the output? Output is taken between the collector and this is the, across this you are going to measure output voltage V0, right? The emitter base junction is forward bias and collector base junction is reverse bias, right? Sorry, here this is collector emitter junction, that is output junction. So, input junction, that is emitter base junction or base emitter junction, you can say, we can say emitter base junction, base emitter junction is forward bias and the collector emitter junction is reverse bias. So, this is for the setup for amplification of the signal. So, the main key features of this CE configuration are, so it has high voltage gain and high current gain and high power gain. So because of these features, it is very used frequently. Applications of CE configuration or high frequency applications like RF amplifiers, radio receivers, signal processing techniques, and then oscillators, etc. So depending upon different configurations, among all these configurations, CE configuration is very frequently used for the applications. So let us see in detail about common emitter configuration. So circuit diagram, if you see this circuit diagram, emitter, this is emitter, base, and this is collector. So emitter terminal is grounded here, so hence it is common emitter configuration. Here the collector emitter voltage VCE is kept constant at 0 voltage. So what is this VCE? So that is VCE means this one, output section. VCE, this is the VCE, that is collector to emitter voltage kept constant, and the base current IB is increased from 0 in shortable equal steps by increasing VBE. So this is for input characteristics. So we can analyze this CE configuration by taking these input characteristics and output characteristics. So let us see first input characteristics. So input, what is the meaning of input characteristics means? Here particularly CE configuration, input characteristics is, it is a graph drawn between input parameters by fixing the output voltage VCE. So that means the collector emitter voltage VCE is kept constant at 0 volt. The base current IB is increased from 0 in shortable equal steps by increasing VBE. So now VBE means what? So what are the input parameters here? Input parameters means here VBE, comma IB, base current and base to emitter voltage. So these are input parameters. So input characteristics means it is a graph drawn between input parameters VBE and IB. So on y-axis we take IB, on x-axis we take VBE. So therefore, if you see the graph of the input characteristics of CE configuration, we have already discussed that input section is forward bias and output section is reverse bias. See here, let us say this is NPN transistor. So P is connected to positive here. This is VBB is the biased voltage, base bias voltage, and VCC is the collector bias voltage. Okay, these are the not input voltages, they are biasing voltage. That means just like a foot for the transistor. So to activate your transistor, your external DC supply is required, and then VBE is the input voltage here and VCE is the output voltage here. So here input characteristics is the graph drawn between input voltage VBE and output voltage IB for fixed values of VCE, output voltage VCE. So let us fix VCE at 0 volts. Okay. So when VC is equal to 0 volts, and what is the output side? Output section is reverse bias. So almost output section is reverse bias. So this is NPN transistor. This is emitter base collector. So this section is forward bias. So this is N type, means here minus N for example. And this is N means here minus plus. So minus plus minus plus. So plus is connected to negative means output section, that is collector base section, emitter base collector. So in different ways we can represent this. Base collector emitter. Okay. So NPN transistor, this side will be forward bias input section and this will be reverse bias output side. So this is for amplification purpose. So since output is reverse bias, so there is no current flow. So almost IC is equals to 0. So therefore there is, your transistor acts like a normal PN diode. And we know what is the normal PN diode characteristics. It's look like this, right? So when VC is equals to 0, when Vc is equals to 0, so what will be the, so your transistor acts like a simple normal PN junction diode. So therefore, as we know the basic normal PN junction diode characteristics, the current starts rising from cut-in voltage. So let us say this is the cut-in voltage. Let us say germanium is the material used to manufacture this transistor. So therefore, from 0.4, your current rises abruptly when Vc is equals to 0. Whereas now let us increase VCE, this reverse bias voltage. If we increase this reverse bias voltage further, what happens? So that means there is a concept called early effect or base width modulation. So in that case, here if you increase this reverse bias voltage, the base width between collector and emitter will be increases. So like this. Let us say NPN. Okay. So this side the base width will be increases. So this is the actual base width. Okay. Actual base width. And now we are increasing this reverse bias voltage. That means the depletion region between this PN junction increases. So that means effective base width decreases. Actually, because of this reason, the IB value decreases. If you increase VCE, IB base current is decreases because IC 0. So in such case, what happens? Base current decreases. So in order to reach the same value which we have got previous, we need to increase the input voltage VBE in order to get the IB value further. So we require to increase the input voltage VBE, hence the curve shifts towards the right like this. So this is about input characteristics of CE configuration. Now let us see what is output characteristics. This is the output characteristics for a constant value of IB. IC is measured for increased collector base voltage. So here output characteristics of CE configuration is nothing but it is the graph drawn between output parameters for fixed values of input current. So that is here, what are the output parameters here? IC and VCE. So output characteristics of CE configuration means, so here it is emitter. CE configuration means graph drawn between IC and VCE. So VCE on x-axis and IC on y-axis. So IC versus VCE for fixed values of input current IB. So when IB is 0, let us say starts from IB equals to 0 microamperes. So when IC equals to 0 microamperes means IB equals to 0 here. So IB equals to 0 means, so we know IC is equal to beta IB. So IC also 0 because IB equals to 0 because open circuited in the input section because IB equals to 0 microamperes. So there is no current flow. Okay, there is no required to VCE. We don't require VCE to supply. So therefore, but still there is a current that is due to minority charge carrier, or you can say reverse saturation current. So that is up to the very low value. So this area is nothing but cutoff region. So if you further increase this IB value, input base current value, so next you will have this kind of graph for, that means IB increases, correspondingly your IC slowly increases because this is the condition. Because the relation between output current IC and input current IB is IC equals to beta IB. So IB increases input current, so correspondingly your IC also slightly increases. And if you further increase the VCE value, there is no increase because it's reverse bias, but your collector current reaches saturation level and it will be constant. But if you consider the common base configuration, so they are exactly constant, horizontal or parallel to the x-axis. Whereas in this case, CE configuration, this is for CB. CE configuration, there is a slightly change like this. So there is a slight slope. If you consider this, there is a slight slope here. So that means there is some increase in the color IC. When we increase this input current IB, so there is an increase in the IC value. And see here, you can observe here. So this is the slope delta VCE by delta VCE and delta IC. So on y-axis we have delta IC, on x-axis delta VCE. So change in VCE by change in IC. So this represents another parameter. So we will discuss later while discussing about the transistor parameters. And this region is called saturation region. So where we don't require, so very small amount of VCE, the current rises abruptly. So very small amount of VCE, the current rises abruptly, and this particular part can be used as can be termed as saturation region. In this region, your transistor works as a on switch. So here in cutoff region, your transistor works as off switch. So between this in the middle, so your transistor act as an amplifier. So this is called active region. Okay. So this is output characteristics of the CE configuration. And what are the consequences we can say? So for large values of VCE, due to early effect, a very small change in alpha is reflected in a very large change in beta. Because, so what is alpha here? In common base, alpha is equals to output voltage by input voltage. So in common base, what is the output? IC, and what is the input? IE. So if you recollect common base configuration, so the alpha is the amplification factor, that is IC by IE, and its alpha value is usually from 0.985 to 0.99 something. So it is less than 1. Whereas this one, so for example, beta, in case of beta, what is beta? Beta is the amplification factor in case of common emitter configuration. Beta is the for common emitter configuration, and this is given by alpha by 1 minus alpha. And output current IC, so this output current IC can be represented by applying KVL in the output loop. So we can get IC is equals to 1 plus beta IC B naught plus IB. So this is the output current in case of your common base configuration. So from these from these equations, we can say how the beta gets affected by change in the alpha value. So alpha is equal to 0.98. So beta will be, so if you substitute in this expression, so you will get 49. If alpha increases to 0.985, previously it is 0.98, now it is 0.985, then beta equals to 0.985. If you substitute in this, so you will get 66. What do you mean by this? So if alpha increases, then beta increases slightly. So there is a drastic increase in the beta value. So this is the consequence of output characteristics. So in output characteristics, your CE configuration of output characteristics have 3 different regions. Those are active region, saturation region, and cutoff regions. Now coming to the transistor parameters, hybrid or H parameters of CE configuration. So the parameters have different dimensions, hence we can say it is hybrid parameters, H parameters. So the input impedance, which is represented with HIE, slope of the input characteristics. So actually HIE means input impedance, means it is the slope of the input characteristics. What is input characteristics? This is the input characteristics which is between VBE and IB, right? Input character. So therefore, we can write HIE is change in VBE by change in IB when VCE is constant. This is VCE, right? Similarly, output admittance, HOE, it is the slope of output characteristics of common emitter configuration. So what are the, this is the output characteristics of common emitter configuration. On x-axis VCE, on y-axis IC. So from this we can say HOE is given by delta change in collector current by change in VCE, delta IC by delta VCE for fixed values of IB when IB is equals to constant. So that is about output admittance. Similarly, forward current gain HFE, it is the slope of the IC versus IB because its value ranges from 20 to 100. So it is IC by IB. HFE means current gain. Current gain means output current by input current. So in CE configuration, what is the output? IC. What is the input? IB. So delta IC by delta IB when VCE is constant. So this is forward current gain. Similarly, the other parameter is reverse voltage gain, HRE. It is the slope versus VBE versus VCE. So reverse voltage gain, usually voltage gain means V0 by Vi. So here reverse voltage gain. So reverse voltage gain means Vi by V0. So for CE configuration, what is the Vi? VBE is the Vi. This is VBE and this is V0 is VCE. VCE, VBE. So therefore we can write HRE is change in VBE by change in VCE when IB is constant. So these are the different transistor parameters for CE configuration. Okay. So let us conclude for today's session. So we have started with BJT configurations. We have common base configuration, common emitter configuration, common collector configuration, and analysis of common emitter configuration we have seen, and then we have seen different transistor parameters, H parameters of CE configuration. So next topic will be analysis of CC. Thank you.